Can you see the correlation between me doing this and the simple maths that are on the board there? So this is an incredible matte painting done by Ralph McQuarrie for Star Wars: The Empire Strikes Back in 1980. Now, isn't that just the absolute pinnacle of visual storytelling and movie magic? I'm from a generation where I've only ever done digital compositing on a computer. I never used glass plates. I was thinking, on a computer screen, you don't have multiple layers of pixels. You only have one layer of pixels, and a pixel can only be one color or another. So how does it work? You can't really crush these into each other and cheese grater the colors together. I mean, that just doesn't work. So when I was writing my own compositing software, which I call Plate Matcher, which I use to show directors and actors like a rough version of the visual effects live, and they love that, by the way, because actors, they love something to react to, and directors want something to direct. If they're just looking at a green screen or a blue screen or a monster that's not there, they can't really do their job. I had to go and program this in from scratch. I really had to make it. It's kind of like if Nuke, After Effects, Photoshop, Fusion, Flame, if they all disappeared and you had to remake it again from scratch, this is the maths you actually had to use to bring in the ability to do things like these autumn matte paintings. The first thing I did was, how about I just add the pixel values together, kind of like A plus B. But the problem with that is that it just gave me a really bright image. Here's the next part of the logic. Hopefully a lot of you are screaming out at the screen now. You know exactly what this is. This is an alpha matte. You're very aware that what is white is what we keep and what is black is what we delete. Now let's think about this. If we want to get rid of this, like we want some transparency, how about we make this section all black, just as it is here? That way, if we can make this black, remember there's no transparency on the computer screen. Every pixel must have a color. But what we could do is we kind of like pre-multiply this with this. So when we do add them together, we get the result that we expect. And that is how you can do a basic composite. We can even take live camera streams. If you see the video that I did last week where I took camera heights in a car and we composited those together live, you can instantly see where the problems in perspective are, and you can make the right choice during production, and you can film everything correctly and professionally. So when we get back to the editing suite, everything just works and there's no nasty surprises. So that is the beauty of being able to do these kind of things on a computer. We can use live streams. Very important for me for an on-set VFX supervisor. Remember, every hour on set on the productions that I work on costs about £10,000 per hour. I don't want to be wasting any time. Where I'm going with all of this is because when I was growing up and we were going through high school and I was doing maths, I wasn't very good at it. We'd be learning about trigonometry, which is through right angle triangles. Let's say there's 4 steps to teaching trigonometry. I wouldn't get step number 2, put my hand up and say, "Miss, could you go over step number 2 again? I don't quite understand it." And then she would say, "Sam, you're an idiot, just carry on." And I think that's not very nice. But then I'd also look around and everyone around me, they get it, and they were typing all the numbers into their calculators and getting the right result. And then when I do my homework, the red pen would come out and get across like wrong, wrong, wrong. So I started getting some really negative associations on top of being publicly humiliated a few times in my class. The way that they teach maths in British high schools is that we have this mnemonic. It's called SO, CA, TOA. Right? SO, CA, TOA. So you use a sine wave, a cosine, or a tangent wave. And when the teacher showed this on the board, and at least she did draw it on the board, it was this curvy thing. And I thought, how does this curvy thing relate to that straight thing? I mean, I just couldn't get it. And when I asked about this, what has that got to do with triangles? She just told me to shut up, basically. Just type your numbers into the calculator and then it works, right? Maybe she was just waiting for a pension. I don't know. So anyway, I just couldn't resolve in my head how this curvy thing resolved with the straight thing. And it wasn't until 20 years later when I saw this diagram, this animation, and it shows you exactly how a sine wave and a cosine wave relates to a circle. So when you split a circle up into an X and a Y axis, you can fit any right angle triangle you can imagine in the whole universe into this circle. And that is how you relate this curvy thing to this straight thing. Let's take something else that people take for granted, which is just moving an image left and right, like on an X-axis. Some of you might know what this is, but this really scared me when I first saw it. This is called a transform matrix. Now, remember I said about moving an image left and right, like on an x-axis? Check this out here. See how it says TX and TY? Yeah, that's an x-axis, left and right, and then a y-axis, which is up and down. Let's say that's offset from 0 by 100 pixels, and we want to say move it another 200 pixels over there. We can take the original position of that pixel, and then we can multiply it by this transform matrix. We will substitute 200 into where TX is there, and then we'll get a position of T300, and Y is still equal to 0. And if you've got a really powerful graphics card that can do all this great stuff, it can do real-time rendering and all that kind of thing, most of what your graphics card does is just multiplying this thousands and thousands or millions of times every second. That's most of what it does. If you can do 2 times 3 equals 6 and 6 plus 3 equals 9, you can do matrix maths. It really is as easy as that. There's another one for rotation as well, and all you've got to do is multiply all of these matrices together, and then the image moves exactly as you expect. It's absolute magic. Computers, which really are just giant calculators, and it gets to the point where we don't even need to know how this is done, but having an appreciation of what happens will make you into a much better artist. Another mathematical formula that's often thrown around but not really understood by many is the inverse square law, and that's commonly denoted for film, like having a lamp and see how things get darker or brighter based on how far they are away from the middle of the light. And all the inverse square law is about how the surface area of a sphere changes as you get further away. So imagine you have 1,000 ball bearings all compact in like one ball, and then they explode outwards. Now, if you have a 1 meter square board that's 1 meter from the middle of that explosion, then maybe 100 ball bearings will hit that board. Now, if you take that same board and move it to 2 meters, now only 25 of those ball bearings is going to go and hit that board. Think of each ball bearing as a photon. So if you've got 100 photons hitting a board versus 25 hitting a board, which one's going to be brighter? I want to share with you one of the most profound, amazing moments that I ever had with maths. This is like a blow your mind moment. So I'm going to set this motor running here. This is a brushless DC motor. It's usually used in robotics. I'll tell you about the code that I've run on this. It uses something called a PID loop. And what that means is without me telling this motor how hard that it has to push, it'll always go around once per second. 1, 2, 3, 4, 5. So it's exactly correct. Now, if I start putting some resistance on this, it'll still, oh, it burns my fingers. It'll still maintain that. Nowhere did I manually say how much power for that motor to put in. I should be moving at this speed, but if I'm going slower, put in more power. If I'm moving too fast, put in less power. And in the PID controller, that stands for proportional integral derivative, and that's all using calculus, by the way. So that's Isaac Newton's calculus that was developed a long time ago. I can use the integral to set how hard to push. And the amazing thing about this is that as I hold this motor, and you can see from the grimace on my face how much harder it's going to be. Oh, Jesus, I actually can't stop the power of that with my own hand. The magic thing is that I can actually feel the integral building up. And this is the first time that maths really jumped out of being on the page and into the real world. It makes you think this maths stuff, it actually works. You can actually feel with your hand your own maths that you went and typed in. It's absolutely incredible. It's like you've pulled back the fabric of the universe, and underneath all the matter is like these mathematical formulas which actually govern everything. It was such a mind-blowing moment. It's like that picture on the ceiling of the Sistine Chapel where you've got God and man like almost touching fingers. It's just this absolutely cosmic, incredible moment. Yeah, I'm not going to touch that one. So please take it from someone who is about to fail maths in high school to someone who made their own software, and it gave you all these incredible abilities, like the ability to key out live, to move images around, to do a live underdistort, the ability just to think of an idea for a tool and then just make it real. It's incredible. It's like a superpower. So if you've had a bad relationship with maths like I did, what I would recommend is just make something with it. When you make something that really helps you, you make a tool, maths becomes your friend. And it is this cosmic thing that's just incredible once you really get to use it. You don't need to do drugs or do psychedelics if you really get maths, because it is cosmic. It's incredible.